Consider balancing of redox reaction. And in balancing of redox reaction, there are basically 6 steps to follow. So the first thing to do is you have to decide, you have to look at your equation and determine which species of your reactant is being oxidized and which species of the reactant is being reduced. By determining these two, it will help you to bring out your reduction half equation and your oxidation half equation. So in our previous video, we talked about how to determine the oxidation number of an atom or an ion. So you can do well to check up on that so that it will give you a hint on how to determine it. However, we're going to go through it briefly. So this is our example which we'll be using to balance the equation. Now, in balancing, as I said, the first thing is to determine which one is being oxidized and which species is being reduced. So how do you determine that? The first thing to do is to look at their oxidation number. So let's start from dichromate. Now, in this very species, we'll find out the oxidation number of chromium so that we'll see whether it is being oxidized. Now, the oxidation number of chromium in this polyatomic ion will now be, since we are looking for that of chromium, we'll make it to be X. And we have 2 atoms of chromium, that means we'll have 2 times X plus the oxidation number of oxygen is -2, but we have 7 atoms of oxygen, so therefore we'll have -2 times 7. Now, the rule says in determining the oxidation number of an atom in a polyatomic ion is to make the sum total of the oxidation number of the individual atoms in the molecule to be equal to the charge on the polyatomic ion. So that means this whole will be equal to -2. So the next thing to do is to open up our bracket by multiplying -2 times 7, which will have -14. So therefore we'll have 2x minus 14, which is equal to -2. We collect like terms together, we move -14 to the other side. As it is crossing the equal sign, the change of the 14 changes from minus to positive. So we'll have 2x will now be equal to -2 plus 14, which will now be equal to plus 12. Dividing both sides by 2, our x now will be equal to 6 plus 6. So that means the oxidation number of chromium on this side, on the reactant side, is plus 6. So let's find out the oxidation state of chromium on the product side so that we'll know whether oxidation occurs or it was reduction that occurs. So picking up this now, it is already written. If you refer to our rules on determining the oxidation state of an monoatomic ion, we said that the oxidation state of an monoatomic ion is equal to the charge on the ion. So that means the oxidation state of chromium on this side will be +3. So we have +6 on this side and +3 on this side. So it is clear here that this species has undergone reduction based on the fact that the oxidation number has reduced from +6 to +3. So that means this yielding this will be our reduction half. Whereas when we check the oxidation number of ion, here is +2, and the oxidation state of ion here is +3. It is clear that the oxidation state has increased, meaning this species has undergone oxidation. So therefore we'll call this our oxidation half. So at this stage we have already determined which one is our oxidation species, which one that will give us our oxidation half equation, and then which one is our reduction species that will give us our reduction half equation. So what we'll do now is we'll write it out. So therefore, our oxidation half equation, which is still on the first step, we have determined which one is oxidizing and which one is reducing, and so we write out our oxidation half. Our oxidation half equation now becomes ion 2 yielding ion 3, whereas our reduction half equation is equal to our dichromate ion yielding chromium 3. So this is our oxidation half, and this is our reduction half equation. So this is the first step, and then now the second step is to balance all atoms except oxygen and hydrogen. So we'll look at the atoms in both equations and see if they are balanced. If they are not balanced, we try to balance them out, but with the exception of oxygen and hydrogen. So looking at our oxidation half equation, we have one atom of iron on this side and we have one atom of iron on the other side. That means it is balanced, so no need of balancing any other thing here. Then coming to our reduction half equation, we have two atoms of chromium on this side, whereas we have one atom of chromium on the other side, which is not balanced. So step 2, in step 2 we have to balance this. This is already balanced, so we just write it down. Ion 2 given ion 3 plus. But I said the reduction half is not balanced. So we have two atoms of chromium on this side and one atom of chromium on our product side. So to balance this, what we need to do is just to add a coefficient of 2 to the chromium on the product side. So when we add 2 here, you can now see that we have two atoms of chromium on this side and two atoms of chromium on the other side. That means which balance out. There are two atoms here and two atoms on the other side. So this is all for step 2. Then the next step is we balance oxygen by adding water to the side with less oxygen, and we balance hydrogen by adding hydrogen ion to the side with less hydrogen. So we look at our oxidation half. Is there any oxygen there? Basically there is no oxygen, and there is no hydrogen to balance also. That means we write down the same thing. Then checking our reduction half, we find out that on the reactant side we have 7 molecules, 7 atoms of oxygen, whereas we have 0 atom of oxygen on the product side. So we have to balance the oxygen atom in our reduction half equation. So how do we balance it? Based on our second step, it says we balance oxygen by adding water to the side with less oxygen. So on this equation, it means it's this side, the product side, that has less oxygen. So therefore what we will do is we write chromium so to this side that has less oxygen, we are going to add water molecule to balance the oxygen. So however, we have added only one water molecule, but we need 7 atoms of oxygen for us to have a balanced equation. So what we will do is we come and add 7, coefficient of 7 to the water molecule. So if you check now, we have 7 atoms of oxygen here and 7 atoms of oxygen on our product side, which are balanced. This 7 is both for the hydrogen and the oxygen. So that means we have 7 atoms of oxygen here, which balance the number of atoms of oxygen that we are having on both sides. So this is step 3. Then moving to step 4, we balance, we need to balance hydrogen also. Yes, we need to balance hydrogen also. So we balance oxygen. If you look at it carefully, you find out that we've created another problem, which is we've added hydrogen to the product side, which is not present on our reactant side. So based on the rule, it states that to balance this additional hydrogen that we added, we add hydrogen ion to the side with less hydrogen. So looking at it, the side with less hydrogen is our reactant side. So that means we are going to add hydrogen ion to this very side, so that we balance the hydrogen atom in the oxidation, in the reduction half. So now let's balance the hydrogen atom. So we add hydrogen ion to the reactant side because it's the side with less number of hydrogen atom. Okay, let me use green so that we know what we've added. So now we have hydrogen on both sides. However, the hydrogen atoms here we have at 14. How do I get 14? When you multiply 7 by these 2, you have 14. So that means the hydrogen atoms here are 14, while we have only 1 hydrogen on this side. So to balance it, what we will do is we add coefficient of 14. So if you look at it now, we have 14 atoms of hydrogen on our reactant side, and we have 14 atoms of hydrogen on our product side, which balance it. So we've balanced our oxygen, and we've also balanced our hydrogen. So we are done with step 3. So now moving to step 4. Now step 4 says we balance the charges by adding electron to the side with greater positive charge. So you look at both the sides and consider their charges. Now, picking my oxidation half equation. So, let's consider the charges on the oxidation half. On the reactant side, the charge is +2. I got the +2 from here. Whereas on our product side, the charge is +3. So now, you can see that the charge here is more positive than the one on this side. And in balancing charges, we said what we add is electron. And we all know that electron is negative. So to balance this, we add electron to the side with higher positive charge, which is our product side. So that means this equation now becomes now plus electron. So in this case, we only need 1 electron to balance them, because what this means is we have +3 and then ±1. So when you add this, definitely you find out that you have to give you +3 minus 1 will give you +2. And consider the charge here is +2. So by adding 1 electron, we've achieved equal number of charges on both on both the reactant side and the product side. So by that, we've already balanced the charges on our oxidation hub. So let me clean here. Let me clean step 1 and 2. So what we've achieved is our oxidation half now becomes so the charges on our oxidation half is now balanced. However, there are situations whereby you find out that you need more than one electron to balance the charges. Now take for instance, we are having, let's say, here to be, let's maintain +2, whereas here we have the charge to be +5. You see, for us to have +2 on this side, we need to add 3 electrons. When you add 3 electrons to +5, you end up having +2, which will balance. So what will determine the number of electrons you are going to add is the charge you are having here. You have to do the mathematics to find that exact number of electrons that will help you to balance out. So we've already balanced the charges on our oxidation half. The next thing now to do is to balance the charges on our reduction half. So our reduction half equation is equal to our dichromate ion plus 14 hydrogen ion to give okay. So this is the reduction half equation. So what we are going to do is to balance the charges in our reduction half equation. So let's find the total charge on our reactant side and then the total charge on our product side. So the charge we have here for this species is -2, and for this one we have +14. Whereas on our product side we have 2 times 3, this +3. You're not just going to write the +3 because it has a coefficient of 2. So you multiply the +3 by the coefficient that we have here. So this now becomes +6. That's this 2 times +3 will give you this +6. Here is water, it has no charge, so it's 0. So when you look at this side, it will give us a total of +12. When you do -2 plus 14, you have +12. While here you have +6, a total of +6. So the charges are not balanced. Here is greater than this. The reactant side is greater than the product side. So how do we balance it? We do the same thing we did here. We add electron to the side that is more positive. So since here is +12, so how many electrons do we need to balance it so that we'll have, on both sides, we'll have equal number of charges? So when we add 6 electrons to 12, electrons is minus. So that means we'll have +12 minus 6, which will give us +6. So when you look at it, by adding 6 electrons to this equation, we will have equal number of charges on both sides. So let's go ahead to add the 6 electrons to our equation. So now our equation becomes Then, since we've already determined that we need 6 more electrons to balance the charges, we go ahead and add that 6 electron to the side that is more positive, which is our reactant side. And then our product still remain the same. So if you look at it now, if you consider the charges on both sides, you'll find out that the charges are now equal. Let's check and see. Here we have -2. Here we have plus 14. 14 times 1, that's how we got the plus 14. Then our electron is negative, so we have -6. While on this side, the charge is 2 times this plus 3. Now this will give us plus 6. Whereas if you do the math here, -2 plus 6 will give us plus 4. Then plus 4 plus, okay, sorry, this is not part of it. It's -2 plus 12 to give us plus, -2 plus 14 will give us plus 12. Then plus 12 minus 6 will give us plus 6. So the charges on the reactant side is plus 6, which is the same thing as the charge on the product side plus 6. So we've successfully balanced the number of electrons on our product side and then on our reactant side. So let's write out our oxidation half equation and our reduction half equation that will balance the two charges. So our balance, let me use green. Oxidation half now, after balancing the charges, will now be, and then the charges are also balanced. We have plus 2 here, and when we sum this up, give us the same plus 2, just like we've seen. So then the next thing is to multiply both half equation by an integer such that the number of electrons on this side will be the same as the number of electrons on this very side of our reduction half. So what I mean is we look for a number that when we multiply oxidation half, it will give us a number of electrons that will be equal to the number of electrons in our reduction half. So let's do this together. We are now in step 5. So when you look at it carefully, we have only 1 electron in our oxidation half equation, while in our reduction half equation we are having 6 electrons. So what is that number that we will use and multiply our oxidation half such that we will have, at the end of the day, we will have the same number of electrons that is present in our reduction half? So it's quite simple. When you multiply the oxidation half by 6, definitely at the end of the day, we'll end up having oxidation, our electron to be 6. So since we are multiplying this by 6, we multiply our reduction half by 1 so that we maintain that 6. So this is what will happen. Our oxidation half, after multiplying by 6, will now become, and mind you, this 6 is multiplying everything in the equation, not just the electron. The 6 will be 6 times our ion 2 ion, which will give us 6 ion 2, and the same 6 will multiply the ion 3, which will give us 6 ion 3. And the same 6 again multiplies our electron, which will give us plus 6 electron. That's our oxidation half. So moving to our reduction half, we said we are going to multiply it by 1 so that we maintain the same number of electrons here. So multiplying everything by 1 is the same thing as writing the whole equation again. So we'll have this down plus 14. This remains 6 electrons to give us plus 7 molecules of water. So that's our final, that's what we finally gotten after multiplying our two equations by an integer such that the number of electrons become equal. So when you look at it now, the number of electrons in our oxidation half is what? 6, right? While the number of electrons in our reduction half still now becomes 6. So we've come to a point whereby now we have the same number of electrons in both oxidation half and in our reduction half equation, and that's the aim. So moving to the next step, which is step 6. Now in step 6 says you add the two equations and cancel out the electrons and other species appearing on both sides. So what we will do now is we will sum up our oxidation half plus our reduction half. After summing them up, we cancel out the electrons and other species that appear on both the reactant side and the product side. So this is what I mean. So summing, just sum of the equation in normal way, just like you sum numbers together. So what we will do is we will write this. Now we have from our reduction half, we have this, so we write it, our dichromate ion plus this from our oxidation half, which is 6, then we have 14 on our reduction half, so we have 14 molecules of hydrogen. We also write it down. So you ensure that all the species you're having on your reactant side in both the oxidation half equation and the reduction half equation are written while summing them up. So let's count. How many species do we have all together in both the two equations? We have 1, 2, 3. So let's see. Have we captured them all in our summation? So let's see, we have 1, 2, 3. So we've summed all the species on our reactant side in both the two equations. Then we move to the product side and sum the species again. So on the product side, we have this. So we write, let's start with chromium. Okay. Plus, that's this one, plus this, which is 6 molecules of iron. We continue from here. So we've written this, which is this one. The next thing we have is 7 molecules of water. So I'll write it here, plus 7 molecules of water. Then our electron, we write plus 6 electrons. So let's check to see whether we've captured all the species in the both equations. So we have 1, 2, 3, 4. We have 4 things on our product side. Let's see, 1, 2, 3, 4. So it's complete. So this is how we sum up the two equations. So after summing the two equations, the next thing is to cancel the electrons since they are the same and they are appearing on opposite side. So we cancel out the electrons we have. So we have 6 electrons here on our product side, and we are supposed to have 6 electrons also on our reactant side. We did not capture the electrons in our reactant side. Now, 1, 2, 3, 4. 1, 2, 3. So that's why it's important to always check. We've not written this electron here. So we're supposed to have plus 6 electron here. Let me write it well. So after writing our 6 ion, the next thing is of hydrogen ion. Then the next thing that we're supposed to write was supposed to be our electron before our product. So now if you see, we have 6 electrons both on our product side and on our reactant side. So since they are on opposite side, we can cancel them out. But it being they are on the same side, which indicates your equation is wrong if at all you come to this stage and find out that all your electrons are on the same side. That means you got it wrong somewhere. They are always supposed to be on opposite side. So since they are on opposite side, you cancel them out. That means now this electron goes with this 6 electron. That's what our statement is saying in step 6. So check again, is there any other atom or compound or an ion that appears on your reactant side and also appears on your product side? If there is any, you cancel it out. So let's go. Okay, we don't have any. This is different from this, so we cannot cancel. We have ion 2 is different from ion 3. It cannot cancel. This is hydrogen ion, which is different from water, so it cannot cancel. So let me give you an instance. Let's say let's assume we have water molecule here on the reactant side. If you check, we have also water molecule on the product side. That means this water molecule, one of it will cancel one that is here, such that at the end of the day you have only 6 molecules. But in this case, since we do not have species that are the same on opposite sides, there is nothing to cancel after cancelling your electrons. So the next thing is to write down your final balance equation. So our final equation now, the balance equation finally will be what we have here, except the things we've cancelled out. So let's say final equation will now be two minus plus So this is our final equation. So after this, it is wise to check and see whether all your atoms are balanced and all your charges are balanced. So here we have 2 chromium. Let's take it out just for check to make sure that you've done the right thing. 2 here, 2 here. That means this is balanced. Then coming to the number of oxygen, we have 7 atoms here. We have 7, so oxygen is balanced. Coming to ion, now we have 6 ions here and we have 6 ions here. That means ion atom is balanced. Then hydrogen, we have 14 hydrogen here. When you do 7 times 2, we also have 14 hydrogen. So all our atoms are balanced. Next thing to check is the charges on both sides. Now on this side we have -2, 6 times 2 plus 12 and plus 14 on this side, which will give us -2 plus 12 is 10, then 10 plus 14 is 24. Now let's check this out whether we have the same charge, plus 24. So here we have 2 times plus 3, we have plus 6, 6 times plus 3, we have plus 18. So when you add up plus 6 plus 18, you have plus 24. So finally, you've seen that we've successfully balanced all the atoms and as well as balanced all the charges. So this is how to balance a chemical redox reaction.